Okay, welcome everyone. You are in the webinar of V2X, EVs Empowering the Energy Transition. I hope that's where you're planned to be. My name is Beverly Deschaux. I'm the president of the Electric Vehicle Association of the Central Coast, and we are doing this in partnership with the Silicon Valley, the first electric vehicle association. And I will be your moderator, and Ben White, who's choosing to stay silent, is handling all the tech stuff. We wouldn't be able to do this without him. And Jerry Pohorsky is the current president of the Electric Vehicle Association of the Silicon Valley, and Ben White is a former president and now treasurer of the Electric Vehicle Association of Silicon Valley. I am joining them in Silicon Valley to make sure I have a good internet connection. We have, this is part of National Drive Electric Week event, and our national sponsors are the Electric Vehicle Association, Plug-in America, Sierra Club, EV Hybrid Noir, and Nissan. Clipper Creek and Electrify America are also sponsors of this event. Our presenters today are Jose Torre-Bueno and Dr. Steve Letendre. Jose will talk about the duck curve and V2X solutions, and Dr. Letendre will talk about his V2X research, the current technology that his company Nuvve has, and examples of future V2G microgrid community resilience hub potentials. Then we'll go through questions and answers. We'll have future visions, inspirations, actions, and final thoughts, announcements, thank yous, and contact information. So Jerry is going to give us an introduction to some of the terms for those people who are here not so familiar with those terms. So Jerry, would you like to?
Yeah, if Ben will put up the slide that has the definitions on it, and I'll just briefly make some comments. I don't want to read the whole thing. So most people are familiar with the grid. I know that we've been having problems here in California when the air conditioning load kind of hit the peak capability of the generating network. So basically, that's what the grid is how everybody gets electricity into their home from these generating stations. Then there's something else called a microgrid, and it's just a small group of interconnected loads and distributed energy sources that are controlled under computer control, software control. And it can be implemented in two ways. It can operate independently of the regular grid that is connected to everybody, or it could also be used in island mode, so it's sort of isolated. Okay, and then there's another concept that's a little different than the microgrid. The microgrid is usually considered to be like a single site. We have something called a virtual power plant. So that's a combination of multiple sites and technologies and assets that are all networked together using some special software and hardware that can be operated, and people can actually make money by connecting their electric vehicle in this type of an environment. And then finally, we have some concept that Beverly really likes called community resilience centers. So this is a public building like a high school auditorium, for example. And if there's some sort of a power emergency or climate emergency, like really, really cold weather or really, really hot weather, people can go there and get air conditioned or warmed, as the case may be. And usually there's food and first aid available and so on and so forth. Okay, if you could scroll the slide to the V2X part now, Ben. Okay, so V2X is kind of an umbrella term, has several subcategories that I'm going to describe next. V2H is vehicle to home. So that would be if you had some sort of an emergency and you wanted to power your home from your Ford F-150 Lightning pickup truck, for example. So this would be in an island mode independent of the grid. Then there's something else called V2L, vehicle to load. So you can take the same Ford F-150 Lightning, for example, and you could go camping, and you could run your microwave oven and a small refrigerator, power tools, lights, a little portable television, and a DVR or kind of a some sort of a player. Then we also have vehicle to grid, V2G, and this is sort of like a virtual power plant, adding to what the regular grid has available in case they're reaching their capacity. So we can supplement the regular grid with this vehicle to grid. And there's a couple ways you can do that. One is just providing energy, but the other one is also providing what they call frequency stability to the 60 Hertz system. So if the grid is under heavy load, that can be sort of compromised, and it could have actually damaged a lot of generating stations in Texas. Could have caused irreparable damage due to that frequency problem. So the vehicle to grid can also help prevent situations like that. And then finally, I have V2V, which is one electrical vehicle charging another one. I test drove a Hyundai Ioniq 5 earlier this year, and it has that capability. So there's a little $500 adapter that you can purchase, and then you hook that into your fast charging port, and it allows you to charge another EV that's stranded by the roadside. And Kia EV6 also has that capability. And like I mentioned earlier, the Ford F-150 Lightning has that. One thing to realize though is that the V2V and the V2L, they can be done just with a single vehicle. You don't need to be connected to a big network. V2H, you actually have to have some stuff done to your home. You can't just automatically plug your F-150 into your truck and then run the whole house off of it. It's going to take some extra things. And then V2G, that's typically not a one vehicle to another entity like a home or another vehicle or to a load. It's actually a much larger network, and it involves something called bidirectional power that our experts are going to talk about in more detail. So you need not only bidirectional power in the vehicle, but you also need that in the charging stations. And then there's some software that controls all of this. So at this point, I'm going to turn it over to our guest speaker.
Oh, actually, it's going to me next.
Okay, sorry.
So that's okay. I actually realized I didn't fully do my intro. A concept that I'm really enjoying now using is what we're calling the EV mobile battery storage unit. But that's what our EVs can now be. And I so look forward to our presenters talking about it. But one of the things that is holding up our transition to renewables is storage. We're just not having enough storage. And so the grid insufficiency can be attributed to lack of storage. We have, in California, we have more solar energy coming into, I'm sorry, Jose will talk about that. Anyway, so that's what our EVs will become. Our EVs will become mobile battery storage units. And both of our guests will talk about how that exactly will play out. So first we'll hear from Dr. Torre-Bueno, who is a technical manager and inventor of the green energy industry. He's a prolific inventor with over 40 issued and pending patents, one of which is to optimize the energy improvements to a building. He has over 30 years of experience. He has been a driver of groundbreaking product development for the emerging technology, green technology, and biotech industries. He left the for-profit sector and now has his own nonprofit called the Center for Community Energy, a nonprofit dedicated to promoting distributed energy systems, including acting as an intervener before the California Public Utilities Commission. Please welcome Dr. Bueno.
Thank you, Beverly. I'm going to share some slides here. Let me see if this works. Yes, I hope everybody's seeing some slides. So I'm going to be talking, as Beverly said, about of vehicle to grid as a method of managing the duck curve. And I'll have to explain what the duck curve is. As Beverly said, the Center for Community Energy is a nonprofit focused on the energy transition through electrification and grid strategies, especially local microgrids. We're particularly interested in putting energy generation in the hands of individuals and communities, and taking it away from the current investor-owned monopoly model. And as she said, we are interveners before the PUC and the Federal Energy Regulatory Commission, meaning we're supposed to speak for the public, and they may or may not listen, but at least we speak. So the issue is California has some very ambitious climate goals to have millions of electric vehicles. Most recently, the goal has been raised to 8 million electric vehicles by 2030. And an ambitious goal to have the energy be renewable or carbon free by 2045, and their intermediate goals too. And recently the goal has been added to do this without leaving behind underserved communities. So what's the duck curve? Well, the duck curve is this curve of the amount of energy that has to come from non-renewable sources. What we're looking at here is the variation of the total energy and demand in California over the course of a typical day. So this is hours of the day. And the light green curve is the total electric energy demand. So it reaches a minimum in the early hours of the morning. And then it rises in the morning. And then it reaches its peak in the evening when everybody goes home and turns on their air conditioner and their television and whatnot. But this is the total demand. And this purple line is the demand that's not met from renewables. And the reason this goes down in the middle of the day is that California now has enough solar energy between what's on people's roofs and the large scale solar commercial scale plants that the utilities own, that much of the demand in California in the middle of the day is met by renewables. And the amount that has to be met by fossil fuel plants goes way down in the middle of the day. But then what happens is in the evening, as the sun sets, the fossil fuel plants have to be ramped up. And somebody in the agencies that manage the grid thought that this looked like the back of a duck. And they said, oh my gosh, our demand curve is looking like the back of a duck. And this stuck, and it's now become a term of art. And everybody responsible for the management of the grid agonizes about the duck curve. And specifically about this ramp of how fast they have to ramp up fossil fuel plants. So this issue of how are we going to power the state as the sun sets has become the sort of driving issue in the management of the grid. And this is the same issue viewed from the production side. This is for a typical day, for a specific day actually. The green is the sum of all the power that could potentially be produced from every power plant in California if they were all turned on. And it's flat, and then it rises in the middle of the day because this is the time when solar power plants could potentially produce power. The red is the total demand, actually the total demand plus a 20% reserve that the CAISO, which is the agency that manages the grid, wants to maintain. And so here's a day when the total demand very nearly crossed the line of the total power that could have been produced by turning on every power plant in the state. And when that happens, any utility that's selling power that doesn't have power already reserved on long-term contract has to buy power on immediate contracts from anybody who has surplus power. And, you know, when things are scarce, the price goes up. So here's the wholesale price of power, and it shoots up by a factor of 10 because of scarcity. So again, scarcity, you know, crisis. So this business about what do we do in the evening when the sun sets is this ongoing problem. So what does this have to do with electric vehicles? And the question is, how will electric vehicles charging impact the duck curve? So the California Energy Commission was tasked with modeling this. And this is the first output from their model. This is what their model says will happen in 2030 if the owners of electric vehicles are allowed to just charge it whenever they want. And the answer is the different colors are sort of irrelevant. That's just a type of charger. But the height of this curve is how much demand is going to be added to the total demand by hour of the day when people have millions of electric vehicles. And the answer is, if nothing is done and people just charge their electric vehicles anytime they want, the peak of charging is going to be at the worst possible time, right when there's the peak demand in the early evening when people get home. So if nothing is done about when people charge electric cars will exacerbate the duck curve in the worst possible way. Fine. So go forward. What's already been done is you can modify when people charge their car by rate design. That is, by making rates that change over time. So right now, there are people who have electric cars can get a rate, most people who have it already, where the rate changes at midnight, so it's much cheaper. So if you put a timer in your car or your charger, and it doesn't start charging until after midnight, then you'll save a lot of money. And their modeling says that, yes, if we do that, then what'll happen is people won't charge when they first get home. There'll be this huge spike. This is midnight here. There's this huge spike. And then from midnight till sometime in the early morning, there's a lot of load. And then there's some load during the day when people charge elsewhere. However, what you'd really be better off, since there's actually, as Beverly mentioned, surplus solar power in California these days. There's actually solar plants that have to be shut down on some days. You really prefer that electric vehicles charge during the day. They've started to call this the EV happy hour, and this would be the most preferred thing. In that case, there's less demand at night and more demand in the middle of the day. So right now, the current policy is charge after midnight. So the advantage is, at the moment, there's idle capacity in the fossil fuel plants, and there's idle capacity in the transmission system. So there's no need to upgrade the transmission and distribution system. We run the plants, we distribute it, and people can charge at home. Now, the disadvantage is we're still using fossil fuel to charge the EVs, and that's violating the state's plan to eliminate it. There's a study that just came out, actually, that says that if, as more people get EVs and do this, it's actually going to destabilize the grid. And it's not helping us, well, it's only helping a little bit in avoiding, eliminating carbon from the thing. This is the graph of the amount of carbon that's produced per unit of electricity production. So in the middle of the day, when more of our electricity is coming from solar, we have the least carbon per unit of electricity. In the early evening, when we're ramping up the least efficient plants, we have the most carbon per unit of electricity. Shifting charging from here to the middle of the night, this is the early hours after midnight, is certainly reducing the amount of carbon we're producing per unit of electricity. But it would be better, this is the point of the EV happy hour, it would be better if EVs charged in the middle of the day when the average carbon per unit of electricity is the lowest. So they've actually begun to change the policy. For instance, PG&E now has their most favorable rate from 9 a.m. to 2 p.m., not after midnight. So this policy, where people were being rewarded for charging after midnight, is eventually going to go away. The CPUC's goal is to reward people for charging in the daytime. And the CPUC typically assumes that whatever happens is done by the utilities. So right now, utility scale solar is the least costly power. It's abundant during the day and CO2 free. So they have a model where the utilities are going to build more utility scale solar and wind. The transmission grid and probably the distribution grid. Transmission is high voltage and distribution is after it's gone through community local substations and distributed at a lower voltage. And presumably EVs will be charged while they're at work or shopping or something during the day. Now, the disadvantage of this plan is that all of this, the transmission grid, the distribution grid, the panels and buildings will have to be upgraded, all the way to new conduit in the parking lots. All of this will become part of the utilities rate base, and therefore it's going to become a cost to consumers. And the CEC again was asked to model this, and their answer was yes, there'll be massive upgrades to the grid. This is a CEC, oops, lost my place. This is the CEC's results of the study. Every red line on this map is a part of the transmission and distribution grid, which will need an upgrade in order to support 5 million electric vehicles and the necessary 1.1 million public chargers. So it's going to cost billions of dollars. And other groups have looked at the same thing and came to the same conclusion. Boston Consulting Group is an organization that advises utilities. And of course, in the utility model, the more because of the way utilities are regulated, the more they spend, the more profit they make. So from their point of view, this is a good thing. So Boston Consulting Group advised their utilities to expand their revenue stream by entering the market for transportation electrification, in other words, EV charging. Their model suggests that between $11 and $30 billion just in California could be justified before 2030. Of course, that means if they justify spending money, they justify rate increase. So their report was very optimistic from the point of view of utilities. Of course, for ratepayers, it's not. And even local upgrades, that is upgrades downstream of the local transformer stations, are very expensive. This is the result from a pilot project where the utilities are given permission to install 6,000 public chargers. And it came out to an average cost of $17,000 per charger. And a charger costs about $2,000. So where did the other $15,000 go? It went to what they called make ready. In other words, the cost of bringing electricity from the local transformer station to the charger. So if you translate that to 1 million public chargers, it's about $17 billion. So, these various estimates are pretty much on the money. And the problem is, if you look at your utility bill, you'll see that the cost of transmission is already more than the cost of actually making the electricity. And over the last couple of decades, the cost of transmission has gone up enormously because the utilities are rewarded for spending as much as possible on transmission and distribution. Ironically, there's a quirk in the law that makes long distance transmission is rewarded with a higher return on investment than local distribution. So the utilities are actually rewarded more the more distantly they bring electricity. That's a perverse incentive. In any case, having looked at all that, CEC has an alternative proposal for our organization. And that's basically, if you want the cars charged during the day, put the solar collectors where the cars are. The foodies say eat local, so we say charge local. So in this diagram, all this business is grayed out, meaning don't do it. We don't have to upgrade all this transmission and distribution infrastructure. We say, put the solar over the cars and carport mounted solar arrays. Don't dig up the parking lot to run conduit. Just bring the power straight down to chargers in the parking lot, charge the cars while they're at work. The charger actually only needs enough connection to the grid to pick up the frequency, which saves us, this gets very technical, but the minimum connection to the grid means that we don't have to upgrade the electrical panel in the building. And furthermore, it means that when the car is charged, it can go home. And if the person has a bidirectional charger, this is the V to G aspect, they can run the charger backwards, put electricity into the home, and as we'll discuss later, that's V to G. So the advantages of this, we avoid all this upgrade of the transmission and distribution network. We avoid having to upgrade the electrical panel in the buildings. Importantly, EV owners who don't have charging at home can charge at work. This has been a big issue. It's been recognized that lots of people live in apartments or don't have garages, don't have any way to charge their cars at home. And studies about what it would cost to add charging in apartment complexes come out to would be really, really expensive. And the CPUC has really begun to think this thought. They've referred to, they call this back of the lot charging. The thinking is that businesses, in addition to putting fast chargers for their customers, should be putting slow chargers in the back of the lot where their workers park, because especially the lower paid workers probably live in apartments and probably don't have any other place to park their car, to charge their car. So if they're going to get a chance to own electric cars, they have to be provided with a chance to charge it at work. On the other hand, anybody who does have a charger at home, if they get a chance to charge their car at work, means they can carry electricity home, run it backwards through a V to H or V to G bidirectional charger, and help tame the duck curve. The other beauty of this is the owner of a building can mount these things, can build these chargers and sell the electricity to people. So there's no need to involve the utilities. Now, the disadvantage is that this kind of solar, where it's mounted on a carport, is necessarily more expensive than a ground mount by a factor of 2 or more. But we would argue that when you consider the cost of the upgrades to the distribution and transmission grids that are necessary to bring electricity from far away, the avoided cost of the transmission and distribution makes up for the higher cost of a carport mounted solar array. So we argue that charging locally from local power synergistically solves multiple problems. Most importantly, it eliminates the need to upgrade the grid. For drivers who have a V2X connection at home, it allows them to help tame the duck curve by carrying the energy home to discharge into the house to eliminate the evening peak. For drivers who don't have access to home charging at home, that is residents in multi-unit housing, it allows charging at work, which makes EVs possible. And it provides local revenue and keeps funding local because it avoids utility rate upgrades. So I'm suggesting that there'd be enough power from bidirectional EVs to meet the duck curve. So quick back of the envelope thought experiment. Let's try this. California wants 5 million EVs or more by 2030. Let's assume they have a battery capacity of 75 kilowatts, which is typical for current electric cars. And let's assume they're V2G capable, which is most electric cars on the road right now aren't, but coming ones are having this capacity. And let's assume that they're able to charge at work and that they have a level 2 charger at home. The combined power would be 37,000 megawatts, and the combined battery capacity would be 375,000 megawatt hours. At current prices, that's $52 billion worth of batteries. Now, obviously, they're only going to want to sell a fraction of that stored charge. But keep in mind, the average commute is only 30 miles, and new EVs typically have a range of 300 miles. So let's look at that compared to the duck curve I showed you before. This is the height of the duck curve. 28% of the theoretical maximum discharge would completely cut off the duck curve, which is much more than we need to do. The area here is the total amount of energy it would take to completely cut off the duck curve. That's only 12% of the theoretical capacity of the sum of the 5 million EVs. So A small fraction of the energy in 5 million EVs would be enough to trim the duck curve. So this is a trivial back of the envelope calculation, but it says this is enough energy to be thought about. And the good news is the CPUC has just this year begun to model V2G in its integrated resource planning process. So this is now being considered. Up till this year, it was never considered as part of the model of what we're going to do to trim the duck curve. And I didn't just come up with this. This is a Berkeley study from a couple of years ago where they used 3 million EVs, which were mostly Chevy Volts, which have less power. But they come to the same conclusion. The teal is the original duck curve. The red is what happens if as the CEC did, what happens if you do nothing? It makes it worse. And the green is what happens if you have V2G. And as I concluded, it trims the duck curve. And before you say, boy, that would be really hard to manage to have all these cars trying to feed the grid at once, the software to do that has already been developed. And our next speaker is I'm not going to steal his thunder, just let you know this exists and they're going to talk about it. And I got the slide from them, so that's all I'm going to say about it. Conclusion, the infrastructure for charging a future fleet of EVs is potentially very costly if it's done in an unthoughtful way. Making electricity where the cars are parked during the day could be potentially much less expensive. And allowing EV owners to feed power from the cars to homes or the grid could avoid the duck curve. And therefore, what I say to you is, look for V2G when you buy your next EV. And questions, further information, here's my contact information. And Beverly, do you want me to take questions now or wait till the end?
Let's wait till the end because some of the questions you might each have answers to.
Okay, in that case, I'll stop sharing so our next speaker can take it.
Okay. Something I did not mention is that people are being kept muted. And we ask for you to put your questions in the chat and to please keep them succinct so that we can capture them, and we'll ask them of the speakers after our next speaker. So our next speaker is Dr. Steve Letendre, who works for Nuvve. And Steve is going to talk with us about what technical innovations his company is providing. His company is providing the V2G capability and the aggregating capability for a virtual power plant. Steve is a regulatory analyst and policy professional with over 25 years of experience. Ben, could you put up Steve's bio, please? So I'll keep talking while we're getting that up. Steve's been doing V2X. Okay. Steve's been doing V2X analysis and research for over 25 years, and was thank you. Has done the seminal article on V2G titled "Electric Vehicles as a New Power Source for Electric Utilities" with Willett Kempton, which is well known as a start in people exploring this technology. Steve promotes policy, regulations, and wholesale market reforms that unlock the value of V2G to the grid and customers. And in Nuvve, he is the policy director. So please welcome our next guest speaker, Dr. Steve Letendre.
All right. Good afternoon. can folks see my slide? It's okay and hear me?
Yes, we can see it.
Yes.
Okay. Well, thank you, Beverly, for the introduction and for the opportunity to be here with you all this afternoon. So, Jose, that was a fantastic kind of big picture perspective on transportation electrification, and really an excellent job of framing the opportunity here and around electric vehicles and the transformation of the electric grid to renewable forms of energy, solar, wind, really is an exciting opportunity. There's some really interesting synergies around these resources and thinking of them holistically, which I think Jose did a great job laying out in his presentation. So thank you for that. So what I'm going to be doing in my part of the workshop this afternoon is to really take a deeper dive into the vehicle to grid technology, about what is Nuvve doing in that space, where are we in terms of the technology development, and where do I think we're going to be heading in the next couple years. So that's my goal this afternoon in the next 20 minutes or so. Nuvve Holding Corporation is a publicly traded company, so I do just acknowledge that a legal disclaimer. I'm going to be talking about our company, the technology, and none of that should be, obviously you should do your own diligence in terms of the company and our future. So I just put this up here to make the lawyers happy. So, so with that, I want to just give you a little introduction to Nuvve. We are headquartered in San Diego. I'm actually based in the East Coast. I work out of my home office in central Vermont. But we also have offices, not only our headquarters in San Diego, Newark, Delaware, as Beverly mentioned, Dr. Will Kempton, who I've worked with on vehicle to grid technology. He has a research team there that's affiliated with our company. We've got employees working in Europe and UK and Copenhagen and Denmark. We're still pretty much a startup company, relatively small technology company. I think we're now about 65 employees. But one of the important claim to fame here is that we have been involved in this space for many years. We've got rights to some of the IP that was developed around vehicle to grid systems and technology at the University of Delaware. And we've actually been operating vehicle to grid systems for over 5 years consecutively in Denmark. We're actually aggregating fleet of Nissan Leafs and Nissan minivans, and we've been actually coordinating the charging and then aggregating those vehicles and participating in wholesale markets in Denmark, actually providing, I think Jose mentioned, one of the grid services that's required to maintain reliability is a service that's referred to as frequency response regulation. And we've been doing that in Denmark for a number of years. So we have significant history and expertise, and we are now commercializing that technology here in the United States and elsewhere, and I'll be talking about our approach to that. But first, I wanted to, again, just talk a little bit about where Nuvve sits. We've got fleets of vehicles, whether it's light duty or medium heavy duty fleets. Talk about FedEx, or I'm going to talk a lot about school buses. And then you've got our individual vehicles that we have in our garages and parked next to our homes. And then on the other side, we've got the electric power grid. And so I think Jose did a great job talking about how these two systems historically have been separate and distinct. The two never really met. We went to the gas station to fill up our cars. And now this is all changing as we begin this journey towards electric transportation electrification. So it does require this kind of intermediary. And this is where Nuvve sits. And there are other companies as well that will manage the charging of vehicles. And the first and foremost, electric vehicles are about providing mobility services, bringing people from point A to point B. So as a company, we have a software platform that manages the charging of those vehicles to make sure they're ready, fully charged when the vehicle owner needs to use them for their trips. And then secondly, we understand the grid. And as Jose said, there's the price of energy on the system changes throughout the day. And so we want to deliver that energy to the vehicles in the lowest cost possible and also in the lowest emissions possible. And it's interesting today, as we've noted, solar is the lowest cost form of renewable energy generation. And it's also a very low carbon, low emissions form of energy, zero emissions. And so we can coordinate making sure that we're charging the vehicles at the lowest cost with the lowest environmental impact. And then I think uniquely where Nuvve sits is we have this technology, vehicle to grid, which looks at the vehicles, makes sure that they're charged for the transportation, the mobility services they provide. And then when it's appropriate, we can reverse flow, take that power from the batteries and return it to the grid when it's appropriate. And the concept of charging during the day when there's lots of excess solar generation, then going home and then distributing that, delivering that renewable solar generation into your home during the evening hours, addressing that duck curve problem, that issue where the solar generation declines as evening approaches. And we can address that by using the technology that Nuvve has developed. So again, Nuvve sits in the middle of these two massive complex systems and helps manage and negotiate the charging and discharging of electric vehicles to the grid. So I'm going to get into the weeds a little bit in my presentation this afternoon, and we're going to start off here. And this was kind of covered a bit in the introduction. I wanted to just make sure there's clarity in terms of the different configurations about vehicles and how they can relate to the electric grid. And I'm borrowing these graphics from an organization called VGIC, Vehicle Grid Integration Council, based in California. They do regulatory work on behalf of V2X. They've got members, includes automobile manufacturers, it includes technology companies such as Nuvve and others. And so one of the important distinctions is between energization. You put an EV charger in your garage and you just want to charge your vehicle. You want the utility to provide power for that. So that's what we call A here, which would be load only mode. So 99.9% of the chargers that are deployed today are in that load only mode under this energization. And then we progress to B, which is islanded for backup power. And so this is a system which Ford is marketing through their Ford Intelligent backup power system. And so this is a case where if the power grid goes out, then you can use your vehicle to power your home. It's very comparable to a backup generator. If you have a natural gas backup generator, when the power goes out, the generator automatically kicks in and provides power to your home, rather than using a fuel or a polluting resource such as a gas generator. You can actually use the stored energy in your home, in your vehicle to power your home during a grid outage. And so in that case, the inverter that would be that's a part of this inverter is a device that converts DC power to AC power. And so in that case, that type of technology, that inverter, is what they call grid forming. So when the power goes out, the Ford F-150 knows that the power's out, and it can safely deliver power to the home to avoid any potential risks for utility workers, etc. It's called a grid forming inverter. And as you move to the right, now this is the situation where we talk about interconnection. This is like interconnection of solar or battery systems. The device has the capability of discharging power from the device to the home or to the grid. And so that requires an interconnection. And that has a whole different set of procedures. In California, it's called Rule 21. You have to go through these screenings and procedures to make sure that the technology is certified and it's installed in such a way that it can safely operate. So in this case, we have C, which is parallel non-export. And this is a case where you could still be having power from the grid coming to your home, but you may want to use the energy in your battery in your vehicle to perhaps manage your bills, to reduce the bills that you receive from the utility. In this case, you may charge during low cost off-peak hours, and then displace power that you might consume in your home during higher price on-peak hours, what they call TOU, time of use optimization. So in that case, you're not actually exporting to the grid, you're simply exporting to your home, but you're exporting to your home while the grid power is still available. It's not an outage situation. And the fourth and final configuration is what we call parallel with grid exports, and that would be D. And in this case, you have the electric vehicle that can discharge power to your home. And then if you have more power than your home is currently consuming, it can actually discharge power back to the grid. And that's what most folks think about when we're talking about vehicle to grid, taking that power, that energy stored in the battery in your vehicle and transmitting it back to the grid. And that's what we call V2G. And so both of those configurations, C and D, are grid following. The inverter, that technical device in the system, is grid following. It can sense the frequency on the grid, and it will operate safely in parallel with the grid system. Now, if the inverters on those C and D configurations had that grid forming capability, then in fact, the vehicles could provide that backup power in the case of a grid outage. And that, as I'll get to later, is a functionality that's certainly on Nuvve's roadmap, but I'm not aware of any particular configuration or device today that would allow you to be both grid following and grid forming in a single device. And certainly that's something that's of interest to Nuvve in many different use cases. And we do see that as something that would be available in the not too distant future. But again, today, part of my presentation is to say kind of where are we today? What do we have today that we can go out and do off the shelf, and kind of what do we see coming in the next couple of years? Hopefully that makes sense to folks. So I'm going to mostly talk really about that fourth configuration, vehicle to grid. That's really what Nuvve envisions. We see a tremendous value with the number of electric vehicles coming onto the market, coming onto the grid as providing grid services. That's really where we believe the most economic value, the greatest benefits can be received. And so, in its simplest form, we're talking about charging the vehicle during low cost, low grid constraints, low emissions periods, and then discharging that power back to the grid during periods when it's higher cost, high in displacing higher emission sources of generation. So fundamentally, that's what this technology provides the opportunity to charge at low cost, low emissions, and to discharge back to the grid during those times when emissions would be quite high and when prices would also be high. So we had some definitions early on in the workshop. One of those definitions was this concept of a virtual power plant. And so that's really what Nuvve's technology does. We aggregate tens, hundreds, thousands of electric vehicles. We control those resources, and we can present them to the grid as if it was comparable to a typical centralized large-scale source of generation, such as a natural gas power plant. So we talk about virtual power plant, we talk about aggregation of small individual sources of generation or storage, and then present them to the grid in a fashion which is comparable to what a typical power generation resource would provide. And so that virtual power plant allows those individual resources to be part of the grid, and it also allows them to receive compensation for the services that they provide to the grid. And that's really what Nuvve is working on, is aggregating these vehicles, having these virtual power plants provide services to the grid, lowering costs to the grid, and also providing benefits to the EV owners. So when we talk about the value of V2G, right, we're talking about ultimately we see vehicle to grid as Jose had mentioned, has a key part to this transition to renewable grid. But in the process, it generates value for the EV owners. And ultimately what that means, that's going to reduce the cost of ownership for EV owners, and it's going to accelerate adoption of that technology as the value, the benefits that EV owners receive will justify perhaps the initial higher cost of EVs relative to a internal combustion or a gas vehicle. So there's two different ways that value is generated. One is providing grid services, as I mentioned, delivering power to the grid when it's needed, and the utilities And the grid operators will compensate you for those services. And we're doing that today. I'll get to that later on in my presentation. We are being compensated for V2G systems that we've deployed. And the other way that you create value is by creating savings. So if I can use the power in my vehicle to power my home or my office building, using off-peak power or using the stored energy in my EV to manage my demand on a commercial customer basis, reducing demand charges, that creates real value to the vehicle owner, which can be translated to the vehicle owner. So there's these two pathways to value. There's revenue, and then there's savings. And our technology is designed to create value in both of those ways. So I want to just pause here and just really highlight why this bidirectional infrastructure is so important. As I mentioned before, 99.9% of the chargers that are going in today are unidirectional. They go only one way from the grid to the vehicle. And I believe there are, and I'm not alone in this, there are compelling arguments why we should think about moving towards a bidirectional infrastructure, creating the infrastructure so it can both charge from vehicles and discharge back to the grid. And again, by and large, what we're seeing is unidirectional, and we're missing out. There's lost opportunity. So as we move forward, it's important, I think, for us to recognize the benefits of bidirectional infrastructure and incentivize that so people are making the purchases, future-proofing the infrastructure so that we have this ability to use vehicles as grid resources. First and foremost is bidirectional infrastructure allows, as I just talked about, creating value either through savings or through grid revenues. And that ultimately, if that value can go find its way to the EV owner, that's going to be a compelling value proposition, which is going to accelerate EV adoption over time. And Jose's already gone into this in great detail, did a great job on supporting the integration of wind and solar. We need more storage on the system. And this is widely recognized that as we move towards a renewable grid, intermittent resources, that we need more grid flexibility, and energy storage is the prime candidate to provide that grid flexibility. So California, like many other states, is installing lots of stationary storage. There's lots of storage plants that are being installed across the various service territories in PG&E. San Diego Gas and Electric, Southern California Edison are putting out requests for projects for energy storage. And we believe that V2G is a complement to stationary energy storage. And when you think about it, there's lots of materials that have to be mined and produced and manufactured into these stationary energy storage plus in the EVs. So we believe that there's some important resource efficiency arguments around making sure that we can use EVs as grid storage, therefore perhaps avoiding additional resources that we require to build the stationary storage, which we know we'll need some of that, but again, we believe V2G is a complement to that. And then, you know, there's a lot of talk about resilience, and we do think EVs will play a key role in that, but we believe, and again with V2G, that we want these vehicles to be part of the solution before we have a grid outage. We want EVs to be part of the reliability framework so that we can have a more resilient and reliable grid, and in fact avoid power outages altogether. So we want to use these vehicles during these emergency times when the grid is very strained, like we just had a week and a half ago with that intense heat wave, and using the vehicles to avoid a power outage altogether, we think is the important first step. And then ultimately, when the grid does go down, and it is quite rare, the grid is quite reliable. When it does go down, we do see EVs providing that resilience function, providing essential loads to buildings and other facilities. And again, an EV battery is quite large, you know, 125 kW kilowatt hour battery could power a home for several days. So there really is an important resiliency opportunity there. But again, let's use these vehicles, let's integrate them into the system in a way that we can leverage them and to avoid an outage altogether. Obviously, there are times when storms and other events create outages that are beyond what energy storage could help to avoid. And in those cases, we'd like to see EVs providing that resiliency benefit. So Nuvve has been, again, mentioned. We've been involved in this space for many years. We have done numerous demonstration and pilot projects all across the globe, in the United States and Europe. And I'm here this afternoon to tell you that we are now moving from pilots and demonstrations to commercialization. And that is really an exciting inflection point to really take advantage of this exciting opportunity that we're here this evening to talk about. So Nuvve has two different bidirectional chargers. We have an AC charger called the Nuvve PowerPoint, and we have a DC charger in both 60 kilowatt, 125 kilowatt, which is a fast charger. It's a DC fast charger. Both of these units are bidirectional. However, I'll note here in the next slide that today the only fully certified bidirectional chargers are DC chargers, and they're the only units that are certified and can be interconnected through California's Rule 21, the interconnection procedure. And I'll explain a little bit about the difference between what we call V2G AC versus V2G DC. So this is getting a bit into the weeds, into the technical details. But V2G AC is where the bidirectional inverter, that device that converts DC to AC, is located on the vehicle. So it would draw DC power from the battery pack, and it would push AC power out from the vehicle through the charger to the building or to the grid. And V2G DC, which is available today, as I mentioned, it takes DC power off the vehicle battery, and in the charging station, it's got the device that converts the DC power to AC power and then delivers AC power to buildings and to the grid, which is, of course, is how our grid is based on AC power. And so V2G AC is coming. California has a process where they hope to be in a place to begin interconnecting V2G AC systems. But I believe that still is at least 2-3 years out. They're still in the process of developing the technical standards for V2G AC systems. Those standards should be completed by the end of this calendar year, and then it will take a year or two before the systems are certified for interconnection under Rule 21. But it is coming. V2G DC is available today. We have commercially available products today that we're deploying in California and other locations across the country. So our Nuvve's current commercial offering is a V2G DC system, including our 60 or 125 kW bidirectional DC inverter. And then we've worked closely with school bus manufacturers, both Bluebird and Lion Electric. And so we believe that school bus electrification is an excellent use case for V2G. They've got extremely large batteries. They've got defined routes, and they're often sitting idle for months at a time during the summer vacation, which is exactly when the grid is most in need of excess capacity. So our inverter is UL 1741 SA certified. So that is certified, and it can be interconnected. Again, I've said a couple of those interconnected through Rule 21 in California, and we've installed many of these units in California. And then V2G requires the charger to work with the vehicle. And so it may be obvious, but you have to make sure that they're compatible. There's this interoperability, there's compatibility that's required. So we've worked closely with Bluebird, the nation's leading school bus manufacturer. They have a line of electric school buses, and their buses come off the production line V2G capable, and they're compatible with our bidirectional chargers. Lion Electric is another pure electric vehicle play. excuse me. And they have V2G as a option for the electric school bus. So you can request when you order a bus from Lion that you want the V2G upgrade, and they will integrate that into the system. And we've been operating vehicle to grid systems with both the Lion and the Bluebird electric school buses, and I'll be getting to some of those projects in just a moment. I also just want to note that in addition to Nuvve, which has the technology, the software, and the relationships with the different OEM manufacturers, we also have a joint venture with an investment company called Stone Peak Partners. And we created this joint venture called Levo Mobility, very closely aligned with Nuvve. And they offer a turnkey financing option for school districts, which includes planning, construction management, procurement, and maintenance and training of drivers. It's a turnkey solution. A school district wants to go electric, and this Levo joint venture between Nuvve and Stone Peak Partners can provide the financing, which can go from the beginning of the planning process all the way to construction, procurement, and maintenance of those vehicles. And so we're getting a lot of interest in school districts. It's complex process for a school district to go electric, to electrify their school bus fleet. And so we are a trusted partner. We'll work with them in the planning process, develop that relationship, and see them through to completion. So this is one of our flagship projects. This is with Cajon Valley Union School District in San Diego. We've got 6 160 kW DC fast chargers with 6 Lion electric school buses. And this system was commissioned earlier this summer. And it's very exciting. This is the first V2G electric school bus at scale project that we've seen in California, in this region. And in fact, it's very exciting. Just last week or the week and a half ago, this combined buses with the chargers in collaboration with San Diego Gas and Electric as a pilot program has been participating in California's ELRP, which stands for Emergency Load Reduction Program. So when we discharge power to the grid, when the utility needs it, the utility will pay us $2 per kilowatt hour for every kilowatt hour that we deliver back to the grid. So it really is a full compensation for vehicle to grid exports. We're delivering power back to the grid, and we're being compensated by the utility providing that service. And so this was earlier this month when we all recall California was hit by another intense week or so of extreme heat, and there were multiple ELRP events. So the ELRP events are emergency events when the California ISO, the grid operator, says we're running low on capacity. We need everyone to do what they can to contribute to maintain reliability of the system. They send out an alert, utility contacts Nuvve, and then we dispatch the power to the grid. Typically it's from, I think, 4 to 9 o'clock in that time range, which is those charts that Jose showed. That's the period of time when the peak demand is at its highest, the solar is declining, and people are using energy when they go home for their air conditioning and other appliances. So very excited. This was a big milestone for us to have a fully functional vehicle to grid system in California responding to these emergency events and creating real value for the school district. So we're just getting started. We have a number of other projects that are under construction and also planned. There's 2 more in addition to the 6 units at Cajon Valley. We've got 2 other phases. We'll be expanding the electric vehicle charging infrastructure, and the school district will be procuring additional electric school buses. We're also working with 2 additional school districts in San Diego Gas and Electric's territory, Ramona and San Diego. And we have here, the Ramona will be 8 60 kW DC fast chargers with 8 Bluebird buses. And again, that project, once it's commissioned, will be eligible to participate in the emergency load response program. San Diego United School District, another which is another project that's under development, which includes 3 DC fast chargers plus 13 level 2 chargers. So we're, I believe that is currently under construction. And then we're also collaborating with PSE&G here on the East Coast on Long Island in New York State. They'll be installing 11 DC fast chargers with 11 Bluebird school buses. We're waiting on some equipment to complete that construction of that project, which we expect to have by the end of this year. So these are ones that are currently planned and under construction. We're seeing a lot of interest in this technology. And again, this is really just the start of, which is going to be a massive growth and opportunity as we see more vehicles, more charging options. And eventually when we get to that V2G AC in 2 or 3 years, I think we'll see really exponential growth. And really it comes down to this understanding that the batteries that are being manufactured, the vast majority of those batteries are going to go into vehicles. Some of those batteries will go into stationary storage, but the vehicles represent just a massive amount of storage capacity. And in thinking of that creatively about how can we create the bidirectional infrastructure that allows us to harness that tremendous capacity to provide reliability for the system. So this is my last slide. Great progress has been made, but there's certainly more that has to be done. And as the director of policy at Nuvve, that's my job, is to make sure that we have growing opportunities for our technology for these systems. And in many parts of the country, there aren't incentives or compensation for V2G exports. And so California has the ELRP, New York State has the VDER tariff, which is available, but many utilities, many other states have no mechanism to compensate the value that V2G brings to the system. Interconnection, these are devices that have to go through a utility process to interconnect so they are allowed to export to the building or to the grid. That can be very time consuming. It can lead to months of delay in projects. We need to streamline that. Glad to see, as Jose mentioned, that the CPUC is beginning to model how V2G plays in the entire grid system. And so we need more analytical tools, more analysis to show what V2G is capable of doing in terms of providing reliability to the system. And then, as I had mentioned before, I really, we're investing all this money in infrastructure and charging infrastructure, and we need to really make sure that we understand the value of what that bidirectional functionality is and create the incentives that move us towards investing in more of that bidirectional capability. We call that future proofing. We don't want to strand all these assets that might be unidirectional and won't be able to provide the value that vehicle to grid can offer to the system. And there are still work is happening on standards and communication protocols. As I mentioned, the V2G AC, they're still under development, the standards. There are some competing kind of communication protocols. So there is a need to kind of, for interoperability and moving quickly towards the standards and technical standards and specifications, the communication protocols that allow this to be widely adopted. So hopefully that was helpful for folks. I know a lot of technical stuff there, a lot of information. I'm going to throw up my contact information and I'll kick it back to Beverly or Jerry, and I'm happy to stick around and answer some questions. And again, I appreciate everyone's time this evening.
Thank you, Stephen and Jose.
Thank you,
There are-
Steve and Jose. Ben has stepped away. He has a newish dog who requires a great deal of attention. So he's had to take the dog out. So I don't know how to make the slide come up for what I was going to say afterwards. What motivated me to organize this webinar is that we have a need for adaptation. So my idea was these school buses with the very large batteries, oftentimes sitting, they're able to charge up in the and be available to take the children to school. Then they're sitting. They can be charging by solar during that time. Then they take the children and then they come back and there's still time for them to be charging by solar. What we can do with that, ideally, would be to, if the schools have multiple buses or if they only have one bus, that energy can go back into the school system itself, the school, not school system, but the school, to provide a microgrid situation. In Santa Cruz, our civic center is set up for emergencies. They have cots, they have food, there's internet connection where people can go. Unfortunately, they don't have solar yet. But with this, each school could become its own little microgrid and could become a community resilience hub where people can go during emergencies, not just when the grid goes down, but during fires, when people are evacuated, during floods, when people are evacuated. We need that as an adaptation role. There's the puppy, said pup. Excuse me, Ben, if you could bring up the slide that for me, if you have a chance.
Yeah.
Yeah.
Okay, yes.
Okay. So that's my idea. And there are people, I keep putting this idea out and people are saying, well, there isn't going to be enough energy to do that. I don't know what the figures are on that. Maybe Steve could speak to that and Jose could speak to that. Jose, I think, has the figures for California of how much he's already presented in his presentation, how many megawatts of energy would be available, but I don't know what the smaller megawatts are. So yes, here's the model here. The school buses being charged by solar. Most of the schools in our city and county have solar at the schools. And that's something for people listening at other parts of the country to be working on with your grid, with your schools. So there's the model, and I like it. I thought it was going to be, hey, I'll just give people this good idea and they'll say, okay, let's do that. But I'm a bit naive in that regard. I have talked to a couple of our school districts, and it turns out we have 10 school districts, so each of them operates separately. So that's what I'm going to be doing next, is talking to our school districts to have them set it up, although I don't think we will be able to avoid, they're already setting up their charging stations for the school buses that they have, and we probably won't be able to catch them in time for them to set up bi-directional, but that's the next step here. So thank you, Steve. Thank you, Jose. I hope that Jerry has been collecting some questions and answers in the grid. One thing that I wanted to ask Steve, did you, what are the obstacles right now to us being able to do that? There have been the California Public Utilities Commission, the manufacturers, and various others. So people who are listening from the other parts of the country, the CPUC is the California Public Utilities Commission, and the CEC is the California Energy Commission that people have been making reference to, in case people haven't followed along with that. So Steve and Jose, would you answer that question for me, and then Jerry can present some other questions that have shown up in the chat.
So repeat the question.
The question is, what are the obstacles currently to being able, aside from the technology that Steve has talked about, the technology is being developed for most EVs. Oh, and by the way, somebody asked this in the chat, the new EVs coming onto the market this year do have bi-directional capacity. That's the Hyundai Ioniq 5, the Kia EV6, the Volkswagen ID4 has it. They haven't announced it yet, but we know they have it. Tesla has it, but they're going to do something. We don't know what, but they've always had it, and they're just saying they don't. Other than the technological developments and them being accepted, what are the obstacles to being able to just do it right now?
with respect to the Tesla, there's some controversy about that. Some people who disassembled Teslas thought that the internal inverter was bidirectional. Other people who subsequently did it thought that they had misinterpreted certain chips and that it wasn't bidirectional. So it's not a given that existing Teslas can be software upgraded to be bidirectional. And that's a very important question. With respect to the Volkswagen, I have been told that the Volkswagens are capable of V2G, but it's software locked out in the United States. Presumably because given the lack of equipment, they don't want to sell a car and then have people not able to use the feature. So presumably at some point they will turn it on. The biggest obstacle as I see it is the utilities, basically. In California, the utilities have been instructed to accept bidirectional EV service equipment. The procedure for getting EV service equipment approved is not, as far as I know, Nuvve is the only company that's actually gotten something approved. So I'd actually be interested in hearing how that went, because the procedures are not that obvious at this point. And as more companies introduce their products, which is coming very quickly, it has to be clarified. At the moment, there's a lot of pilot projects going on. As far as I know, Nuvve is the only company that's actually selling product outside of pilot projects. And we mentioned that they're supposed to be installing DC bidirectional equipment under the same rules. And we mentioned Rule 21. That's the rule under which solar inverters are installed. So what the utilities have been ordered to do is to extend their rules for solar inverters to include V2G inverters. But it's not obvious to me that that's fully been implemented. So it's mostly a bureaucratic obstacle. And I will mention one other thing. There's a little bit of confusion. We had that slide where we mentioned the different use cases. Use case 3 and 4 in California are considered the same thing. That is, if you connect the car to the house or you connect it to the grid, even if you don't run the meter backwards, in California, the PUC considers that V to G, even if you never run the meter backwards, because there's continuity to the grid. There's some confusion in that because in Europe, if you don't run the meter backwards, it's considered regulatorily a different thing. And so the term V to H is used in that case. In California, strictly speaking, you should only call it V to H if you've disconnected from the grid via transfer switch, as the F-150 does when it powers the house. And any time that you're connected to the grid, even if you're not running the meter backwards, if the car is connected to the house power and the house is also connected to the grid, that should be considered V to G. But I think that the biggest issues are bureaucratic issues at the utility level at this point. And do we have?
Oh, sorry.
I'll let Nuvve say what they think.
Yeah, no, thank you. Yeah, California is definitely leading on this. They've been supportive of the CPUC, and the CEC have been and I'm relatively new to Nuvve starting earlier this year, but there's been many years of work at the CPUC and at with California Energy Commission to really analyze the opportunity, understand the technology and the certification that would be required to deploy these technologies safely on the grid. And it really is, we need to understand that utilities have, I agree there's some resistance on the utility side, but really utilities are concerned about any device that's connected to their system and the potential that that device could export power in a way that wouldn't be safe And if there's a line worker that's out there working on the line, then, we need to make sure we have the procedures in place that there would be no risk that these devices would be exporting power and place those workers at harm. And it's comparable to following on the heels of the solar industry and getting comfortable and confidence in the technology. And I think we're making progress in that regard. Look, everyone is realizing that the system is rapidly changing, and EVs are new. It's a new technology. And, I think as we gain more experience, more confidence, get the proper certification and through the procedures, then, this technology, this opportunity will, I think, be embraced largely by different industry stakeholders. We as mentioned, we worked hard to get our device through certified on the approved inverter lists. And, I do expect other companies that will follow suit. But again, this is really on this cusp of kind of pilots and demonstrations to commercialization, and Nuvve is on the forefront of that. And, again, we expect more companies, more options to emerge in the coming years. In terms of Beverly, your concept about the resilient school district, that is capable today. Like you could actually have a grid forming inverter that was outside of the EVSE, that was a microgrid controller that was maybe linked to the solar or to the building, and you could conceivably use our devices, use solar and the batteries and the electric school buses to create a microgrid. Now I would say the biggest barrier would probably be the cost. That would be a fairly expensive system to engineer and design. But those costs certainly will come down over time, and we could see more opportunities for the type of microgrid configuration that you showed in your graphic there.
Something that I'd just like to say is that the utilities are making a big deal about that. They don't want their workers to be harmed, which of course is perfectly responsible of them to do. However, what we know is that when the grid goes down, even people's solar goes down. It's all shut down. So that's, the concern is that it's going to keep feeding back, and that there are switches now that certain of our people with power walls, for example, are able to switch on the power wall and have it go into their home without any concern to the grid at all. But that's not feeding it into the grid itself. So yeah, that's the catch there. Thank you for that. Jerry, what did you come up with in the?
The first question is from Julie. She was wondering about battery degradation and if lithium iron phosphate batteries would be better off than the manganese cobalt ones that are out there now in terms of degradation. I believe that you guys with your software can actually eliminate any degradation by just withdrawing small amounts of power, but you can answer that.
Yes, Steve, what is that? Steve, what is it? Tell how your technology does that.
Yes, no, certainly, if you want to destroy a battery, you can do it by having, constant, frequent, deep discharges from the system. And so we are monitoring the battery state of health with our technology, and we want to keep the dispatch within a certain level of depth of discharge, from about 20 to 80% depth of discharge. If you were to go beyond that or above that, that certainly perhaps would have an impact on the battery health over time. It is an important question, and we have done some analysis. I had mentioned we've been operating this fleet in Denmark for a number of years with Nissan. We have done some analysis at how using their vehicles, for V2G, what was the impact on the battery state of health. We found in that analysis it to be quite minimal, of 1% or 2%. There is more, I think, research that's needed around that. But again, it's our belief that we are monitoring that, and if you keep that discharge within that certain parameters, that the impact on the state of health would be quite minimal. When you think about the way that an EV battery and an EV car, an EV work, is very rapid charging, rapid discharging when you're accelerating. And so you're really using that full range of capacity of the system. In fact, using it for vehicle to grid is much lighter touch on the battery than it is in terms of driving the EV. And so, we do think that it's important. It's something that we monitor, and we certainly take that into account in our engineering and design of our control system.
Great answer. Julia had another question. She
Wait.
said, "Does the
Excuse me
Do
one
the-
second, Jerry. Excuse me one second. I
Okay.
just want to announce there's a time check. We're at 5:27 now. We said we'd end at 5:30, so just respect it. Our team, is everybody okay to keep staying, and other people can stay if they wish to hear the answers, or they can go. Stephen and Jose, are you okay to keep staying and answering questions?
Yeah.
Steve?
I can go
Yeah,
about
great.
another 15, 20 minutes.
Okay.
Okay, now on to Julia's second question. She says, do the utility companies have any protectionist laws to prevent Nuvve's solution? And I add to that, maybe not any laws, but maybe some financial things that they can do to make it prohibitively expensive.
Well, the PUC issued a ruling late last year ordering them to accept this kind of thing under the same rules as they accept solar inverters. Steve mentioned Rule 21. They've been ordered to revise their procedures to allow the installation of V2G systems under their Rule 21. That is sort of underway. Since Nuvve has the only systems that meet all the requirements, it hasn't really been fully tested. As more manufacturers introduce things, especially home level systems, since Nuvve systems are only industrial or sort of large
Commercial.
scale systems, home level systems haven't really been tested yet. But as more manufacturers enter, especially with systems that somebody might use in their garage, we'll see if they've done as they've been told and modified their rules to allow electricians to install systems for people's homes under the Rule 21, the same way they would allow a solar inverter. So we're kind of on the brink of that, if you will.
Okay,
Excuse me, is Rule 21 just for California, or is that federal?
Rule 21, I think, is a California thing,
Just-
as far as
yeah.
I know.
That's just California, but each state has their own interconnection procedures. Many and they vary from state to state, but in California it's called Rule 21. And I would just add, Jerry, to that, fees and expense, can really shift the economics of investing in this type of technology. I know there's some proceeding underway currently about interconnection fees. Right now, solar has, I think, little or no interconnection fees, and there's talk about potentially imposing fees for interconnection of electric vehicle chargers that are bidirectional. That would be problematic depending on the level of those fees. There was a big, I think Jose referred to this, there was a significant new development in California. They adopted a submetering protocol. Many electric vehicle chargers are required to be on a separate meter because if they're on a separate EV rate, or if the customer receives some make-ready funding from the utility, then oftentimes will require that the EV would be on a separate meter, and that can also be costly. And so the submetering protocol is important, and that would allow you to submeter the charging for an EV, be on a separate rate, and not require that investment in a utility grade meter, which could be $1,000 or $1,500. So there are those little costs which can really add up over time and really create a headwind to the technology.
Okay, there's a question from Kevin Bell. He wants to know how much money EV participant could expect from participating in a V2G network. I think that's kind of a broad spectrum there, but maybe you can just kind of give us a general answer.
That's a question that many folks ask, and it's very hard to give an answer to that question. It really depends on the jurisdiction. It depends on the type of service you're providing. So it's really hard to give a concrete number on that. There is a company, Fermata Energy, which has made some claims about what they're able to generate in terms of revenue for a Nissan Leaf. I think they had seen something maybe $600 to $800 per year. But it really depends on the amount of discharging, the compensation mechanism, and the jurisdiction that you're in. So I'm personally not really comfortable giving a specific value for a vehicle per year. There have been a number of studies. I don't know, Jose, if you have any references that you think would be useful to respond to that question.
I don't have them at the top of my head, but I have seen studies that were numbers in the order of $1,000 a year. I don't remember what jurisdiction that was in, though. So it's a little hard to say.
Mhm.
I will put it this way. The charge for electricity in the evening in California is coming up towards 50 cents per kilowatt hour. If you had an EV and you could charge it in any way and then use it to meet your requirements, and the battery in the EV could easily power a home in the evening. You can avoid buying electricity in the evening between 4 and 9. Be easy to look at your bill and figure out how much you're spending between 4 and 9. So avoid, don't think about, I'm going to sell this electricity. Just think about, I'm going to avoid buying electricity between 4 and 9. Look through your bill and calculate how much you're spending between 4 and 9. Think about what the savings would be if you could, use your vehicle to power your home between 4 and 9. And there's a non-trivial savings right there. So that's one way to look at the savings.
Thank you for that. Okay, now we have a question from Kevin Bell again. He wants to know, how much does Lion charge for the bidirectional upgrade?
Yeah, I apologize. I don't have at my fingertips what that upgrade cost is. I don't. It's not prohibitive, but it is. It is a meaningful cost. I would defer to contact a line rep to
Okay.
get a better number on that.
Okay. He has a second question. Are you targeting municipal transit systems?
Nuvve at this current juncture is not. We're kind of laser focused on the electric school bus market initially. We see that as the tip of the spear for vehicle to grid. Transit buses typically, have very high duty cycles. They're operating, 16, 18 hours per day, depending on the transit network. And so there less opportunity to provide those type of grid services.
Okay. Lawrence had another question for the V2G AC use case. Do you need an additional inverter to be in the car, or can your software use the existing electronics in the charger the bidirectional charger to create the AC? And if not, why would anybody want to have the extra weight of the inverter in the car? Just for non-grid use?
Yeah, V2G AC requires a bidirectional inverter on the vehicle, and it's not a very heavy device, so it's not really a weight issue. And in fact, it's not a significant cost either. There are really issues around certification of the device meeting certain standards. The SAE is the Society for Automotive Engineers, has a set of standards and requirements, and then on the off-board equipment, it's UL, Underwriter Laboratory, has standards. And so there's been coordination between those two standard setting organizations to qualify inverters that are part of vehicles that would be able to deliver energy to the grid. So it's really just it's around harmonizing those standards, getting them in place, and then eventually automobile manufacturers will test their devices against the standards, and then they'll certify, and they'll be available again, I think, in the next 2 to 3 years. But it does require the inverter to be on board the vehicle for the AC V2G configuration. and it's not really a big weight or a cost issue.
Okay, good.
Can I clarify something on there? If you have an AC to DC inverter, which you have to have in an electric vehicle, if you want it to be bidirectional, it's not a completely separate device. Many of the components would be shared between the AC and DC side, so that the additional weight and cost isn't a doubling of the systems. There are some new components, but it's not a completely separate, thing that you have to add to the vehicle. That's the reason people have looked at the Teslas and thought that maybe it was actually a bidirectional device in it, because they thought there were components in there that could operate in either direction. The other point I want to make about AC bidirectionality, one of the reasons there's so much interest in AC to grid is that it would allow a vehicle like a school bus to be used as an emergency source of power away from any stationary equipment, so that it could be driven somewhere and connected to a building in an emergency and power that building without that building having had to have some special piece of equipment in it. And that's something you couldn't do otherwise. So there's a lot of interest on the part of municipalities of heavy vehicles like buses, school buses, municipal vehicles having bidirectional AC inverters in them, because they'd be a source of mobile emergency power.
Okay, there was another question about having a separate meter for the EV, but I think you've already answered that. Is that correct?
Yeah, the CPUC recently ruled that the utilities had to accept the built-in meter in the EV service equipment if they're having separate rates for the EV electricity.
Okay, and then
Hang on a second, Jerry. Let me ask Steve something. Steve, do you happen to know if there's a lot of talk right now about EV school bus conversions? Would it be possible for them to have the bidirectional capacity in a conversion?
I think it's definitely technically feasible. I'm not aware of any company that's offering a conversion for electric school buses with V2G functionality. But it doesn't mean that it's not possible. That I'm just not aware of any company that's offering that today.
Thank you. The reason the conversation is going on, of course, because of the current cost of the school buses. So that's why. Yeah.
Yeah, and that cost is largely driven by the volume of batteries that are required. The battery pack itself drives that cost equation.
Thank you.
Here's another question from Lawrence. He wants to know about carbon credits. Can either individuals or organizations that have a larger microgrid get carbon credits?
So California has a low carbon fuel standard, LCFS, and the LCFS is a mechanism that ramps up over time, reduces over time the carbon intensity of fuels, and there are credits that are generated, and those credits can be traded to achieve compliance. And so we do monetize the California's low carbon fuel standards in the projects that we develop. So when you're charging an electric vehicle, you're getting credit because the electricity grid has a lower CI carbon intensity than the fuel that you're displacing. So you're getting credits that you can then sell to monetize the value of that low carbon fuel. I'm not sure if there's I don't believe there's any other carbon credit option that would be available under this configuration.
Okay, Lawrence was wondering about the availability of the V2G bidirectional chargers for CCS. Any time frame when those will be out on the market?
Well, we do have the DC bidirectional with CCS today. Those are available today. A 60 kilowatt and a 125 kilowatt
What about the
device.
AC?
Again, it's my judgment that that's going to be 2 to 3 years before
Okay,
that would be commercially available.
all
There
right,
are
that's
other
about all the,
companies promising home size chargers like 13 kilowatts next year.
okay.
DC.
I don't
DC.
see any other questions at this time.
Okay, so are there any final thoughts from our two presenters? And then we're gonna call it. Jose, Steve, any final thoughts, or you think you've covered pretty much what you want to say?
I'm gonna, before they answer, I'm just gonna say, I think they both did a great job of complementing each other. I can see that there was some collaboration going on between them before the meeting. So it went really smoothly, I think.
Thank you.
Thank you. Yeah, I would just say, this is a huge, it's a transformative process that we're transformative, disruptive technology that we're talking about here. And it's going to be a little messy. It's going to be a little confusing, but I think we're really starting to converge on commercial products that are going to allow us to really tap the tremendous value that electric vehicles provide as grid resources. And so these are really early days. In 5-7 years, I think we're going to see many more products and options out there for consumers. And I commend this group for putting this workshop together. This really is kind of a cutting edge topic. And I really am excited about what the future will hold.
Thank you. Jose, you have any final words?
Thank you all for coming. I agree. This is potentially huge for the grid. I mean, bigger than a lot of things that are being contemplated for the grid. So I hope to see it, grow enormously.
Thank you. I just want to say my final thoughts, which are, I wanted to put this together to inspire people. I would like to see anyone who's on here to go out into your community and speak to your city council, speak to your boards of supervisors, speak to your school districts, speak to your state representatives, and get this going. Introduce them to the topic. Go to your electricity providers. I go regularly and speak to them and say this. And they go, oh, but the technology is not available. Yes, but it's coming. And these are solutions. And oh, we can't do it because we don't have enough storage. Yes, solar, storage, EVs. Yeah, please do that. Join together and speak to your communities to get this going. And also, especially, introduce the topic of EVs as mobile storage units and community resilience hubs that are so essential for the catastrophes that are already happening in California with fires and floods. We have, so I thank everyone for our team here of Ben and Jerry, and I especially thank our presenters, Jose Torre-Bueno and Steve Letendre. And for all of you who have joined, who are probably already doing a great deal in your community. And I thank our electric vehicle organizations, Electric Vehicle Association, Plug in America, and Sierra Club, who are the main presenters for this. And Nissan has been our one of our sponsors since the beginning, I think. Also, I wanted to announce there are still plenty of events happening for National Drive Electric Week. So one of them is our colleague over there, Barry Rand, who's shaking his head. Their webinar will be on Tuesday, a follow-up of what we're talking about here. They will have Ford, the California Energy Commission, and the California Public Utilities Commission, and I'm sure they will answer more of your questions. And that is on Tuesday from noon to 1:30 Pacific Daylight Time. And you can find that, and oh, something else that Barry has put together in San Luis Obispo County, California, is electrifying your life. We had someone do a number of those events of electrifying your home, and those happened on the 12th. Very good, whoever pulled it out. Thank you, Ben. That happened yesterday, that one of our EV guys got 9 different homes to show you what they're doing to electrify their homes, including their transportation. So bi-directional, community resilience hubs, and electrifying your home, those are what's next for us as EV advocates to be promoting in our communities. And I thank you all for your time and attention and for all the work that you do in the community already. And go forth and make some trouble. Thank you.
And power to the people.
Right on. And so we will also, we will have a recording available, and we'll make sure that each of you get it, along with people's contact information. We will send that along to you afterwards. Thank you.
Yeah, probably tomorrow. It takes a while to upload the recording.
Thank you, Beverly. And I did put a link to the Zoom conference for Tuesday in the chat.
So yeah, driveelectricweek.org will have all of the other events. We still have the next coming weekend, and during this week, there are a number of events. So please check them out and get your friends and family to go get educated. Thanks. Bye-bye.
Thank you.
Bye-bye.
Okay, you can stop the recording, Ben.
Ben, are you there? Is Ben still there? Terry?
He was a second ago.
Oh, here he comes.
Good job.
You too. We haven't
Stop the recording. Stop the recording.
stopped the recording.
I thought it will stop when you leave.
Oh, okay. Well,
Oh,
we
okay.
might have some conversations.
Oh. I'm not sure. I can't. Let me.
Well, I'll go ahead and leave, and you can call me back if you want.
Ben's checking out right now how he can stop the recording.
All right.
Okay, good job, team.
It's still going.
I cannot. I've already left. the
Okay.
meeting.
Oh, okay, so Ben already left, so he can't do anything. So we all have to leave, and we can,
Okay, I'm leaving now.
okay, we can have a